Hello my friends, welcome to another assignment video. Here we're going to be looking at GCSE Physics equations. We're going to be looking specifically for AQA paper 1, so looking at the energy topic, electricity topic and particle model of matter. Let's get to it. So this is the big map of all the equations that we need to learn, which are these ones here on the left hand side, and the ones that we're provided on an equation sheet. So let's have a quick run through of these, what they look like and how we're expected to use them. So there are 4 from the energy topic. We're going to break these down as to what they are, what units there are, for example, in a second. Those all have symbols, and we've written out the word equation for them too. And there are also 2 extra ones for efficiency, which don't have symbols. And in electricity, there are 6, one of which is the same as a couple of the equations seen before. We've got the written word equations too, and there is one final one in the particle model of matter. There aren't equations that we need to learn for the atomic structure part of the topic. However, there are written equations, chemical equations, if you like, symbol equations that we have to be able to write for those instead. And the 4 equations you're provided on your equation sheet, these are provided to you in the exam, so you sit down in the exam and they give you a piece of paper that's got these 4 on them. We just need to be able to apply information you're provided to these equations and use them to calculate an answer. So for these 2 equations, they pair really nicely because if an object, for example, has been thrown up in the air, typically all of its kinetic energy will get transferred into gravitational potential energy. That's the energy transfer that's happening, which means that the ball will stop rising up as far. Equally, if you have an object that you push a block off an edge of a cliff or something and it falls a certain distance, falls 10 meters, we can work out how much kinetic energy it should gain and therefore how fast it should go. But let's look at what the equations are and what units there are. So EK is kinetic energy. That's the E for energy, and the type is the small k afterwards. EP is called potential energy, but it's actually gravitational potential energy. Gravitational. And both of these, because they are energy, they are measured in joules. And the letter for the unit there is a capital J. So that's also a capital J. For kinetic energy, we have a half, which I would type into your calculator as 0.5. We have a unit here of mass, which is kilograms, and we have a unit of velocity, which is meters per second. And we must make sure that those units are correct. So if they give it to you in just grams, you have to convert it into kilograms. Likewise for meters and seconds. Must be correct, otherwise you won't get joules out at the end. For the gravitational potential energy equation, we again have grams, kilograms, and for G is a measure of gravitational field strength. Now on the Earth, that's usually about 9.8, but the unit is meters per second squared. It's the acceleration due to gravity, and so that is 9.8 on Earth. And H is height, and height is measured in meters. Once again, we must be measuring those in kilograms and meters per second squared. Otherwise, the units of joules will not be appropriate. And again, just a reminder that usually in a question where, for example, you've got a child going down a wibbly-wobbly slide, here they are, about to have the time of their lives, they're going to fall a distance of about 10 meters by going down that slide. And once we know the height, which is that 10 meters, we know G, which is the gravitational field strength, we know the child's mass, we can work out their change in gravitational potential energy. And if we know the change in gravitational potential energy, we can work out that that would get converted into kinetic energy, and therefore we know the kinetic energy, we know their mass, we can work out their velocity, which is pretty cool. But if we have to do that, we have to be able to rearrange this equation. So for the kinetic energy equation, the rearranging is actually a little bit more complicated than a standard one. So if we wanted to make V the subject from EK equals half V squared, we'd need to make V isolated. Making it the subject, we're making it isolated alone. So what we'd first do is we would move the half and the m to the other side of the equation, which to do the opposite of the function that would be here, and we'd have to do the opposite of multiply, which is to divide. So we're dividing by those 2, which gives us EK over half m equals v squared. Now that is not making v the subject, that's making v squared the subject. So to make it the subject of just v, we need to square root everything. So we'd end up square rooting this left side and square rooting the right side, which leads us to the square root of ek over half m equals v. And that's really as difficult as a rearrangement as you're going to get. It shouldn't be any more difficult than that. For the potential energy equation, the gravitational potential energy equation, you're just going to be dividing by mg or h, or a couple of those to rearrange the equation. It makes it a lot easier. And it's worth either learning this structure, or if you're confident with the rearrangement and how to do that, then follow the rearranging. But that's probably a grade 7 or 8 skill to be able to do that part. For the second part of energy, we have some equations which link us to power and efficiency, and these are really nice and simple. So for the first power equation, we have a definition of power. Energy is the rate of energy transfer. That's what power is. And in the definition, we can give an equation. So power is energy divided by time, which gives us, if you like, joules per second. And 1 joule per second is the same as 1 watt, which is where that definition comes from and where our equation comes from, because we have joules divided by seconds. Joules divided by seconds is the same as power. Power is measured in capital W watts. The second equation there is just the same as the first, just that we're using a different symbol or different word to describe what energy is in this case. So for the first one here, we have energy transferred, so where it's transferred from one store to another. For the second one, it's where work is being done, and work done is defined as making an object move a certain distance, which is linking to this equation from paper 2, where work done equals force times by s, which is displacement or distance. It's how far we've moved an object using a force. So it is just the same. Work done is still in joules, time is still in seconds, and power is still in watts, but it's just written with a different symbol and written with different words. Efficiency, however, is how well an appliance or something will use either energy or power. You've got 2 equations there from the specification. One is a useful output energy transfer divided by total energy total transfer in, and we've got the efficiency being the useful power output divided by total power input. Really, I would summarize those as efficiency equals the output divided by its input. Now, both of those will give you a decimal. So the most efficient something could become would be 1.0, because that would be the output matching its input completely. Neither of these equations multiply by 100 to give a percentage, but you could give percentage efficiency as an answer, and that would still be a correct answer. And in which case, a perfectly efficient device would be 100% efficient. But there we go. In electricity, we have 6 equations to look at, and the first 3 are all to do with defining electricity and how it behaves, really. So the first equation here, we have a definition of current, which is Q equals IT. And the reason it's a definition of current is because current is the rate of flow of charge. And the rate of flow of charge can be written as I equals Q over T. Now, these 3 equations are written on the page without any division signs, makes it a bit easier to learn. So Q equals IT equals QV, V equals IR. They're not written as the definition would show. But current is defined as its charge per second. So Q is charge measured in coulombs, and time is measured in seconds. So it's coulombs per second. That's what current is. But coulombs per second is actually a unit, which is amps. So there we go, that's what this equation means. So Q is measured in coulombs, I is measured in amps, and time is measured in seconds. That's the definition of current, rate of flow of charge. The second equation here on the right-hand side is the definition of voltage, or potential difference is a better way of putting it. Although in the equation, in the examinations, you can use either term completely interchangeably and they won't mind at all. And voltage is the energy per charge. That's its definition as an equation. And if we rearrange this one that we have here, it's V equals energy per charge. How much energy does each electron or each ion have as it moves through a circuit or through something that can conduct electricity? How do we measure each of these? Well, E is energy, that's in joules. Q again is in charge. Coulombs is charge, it's in coulombs. And V is volts, measured in volts. So we've got two equations, two definitions. Current is the rate of flow of charge, so charge per second, passing a point, passing an appliance, passing a component, whatever it is. And voltage is how much energy does each bit of charge have. And the third equation here is a relationship. It's called Ohm's law. And Ohm's law states that the resistance is dependent on the voltage divided by its current. And this is a relationship of direct proportionality where if the resistance is fixed, so this remains constant, let's call it 1. If to begin with you have a voltage of 1, you have a current of 1. If the voltage is increased to 2, to remain with a resistance of 1 ohm, you must also have 2 amps. And the way that we would write that is that V is proportional to I. And if you were to draw this as a graph, you'd find directly proportional in that it passes through 0 and it increases by the same amount. If you double V, it doubles I as well. And these symbols are really important. You'll have to put numbers in. This is probably the most common to come up in this paper. V again is measured in volts, I is measured in amps, and R is measured in a funny symbol which is called ohms. And for the second part of electricity, we have a very similar equation to one we saw earlier, which is a rearranged version of power equals energy divided by time, because we're looking at power, the delivery of energy over time again. So we won't talk through that one. What we will talk through, though, is how we can actually then calculate power from current, which is measured in amps, and volts, which are measured in volts. Power is in watts, by multiplying current and voltage together. And the reason we can do that is because the definition of current was Q over T, and definition of voltage was E over Q. And if we multiply these two things together, you end up cancelling out the Q's, which leaves E over T. So power is energy over time, but if you multiply current and voltage together, you actually end up with the same thing. And if we rearrange, not rearrange, but if we substitute in for voltage, if we substitute voltage for what it is from Ohm's law, where V equals IR, and we say that instead of P equaling IV, we say P equals I with this IR substituted in for the V, we get this next equation, which is P equals I squared R, because P equals I times by the IR from earlier, from here, we can actually simplify that to make P equals I squared R. So it's just it's substituting voltage for where we have resistance, and it's just showing us how we can change our equations and substitute in other values to calculate things. And in this case, we have power again, which is in watts. We have I, which is in amps, and we have R, which is in ohms. And that's our electricity equations. The last and final equation we need to know is from the particle modeler of matter, and this is for density. And if you think about what density is, it's how much matter there is per volume of the substance. So it's the mass per volume. And the unit for that, therefore, is kilograms per meter squared. And if you look at this unit, it's one of those wonderful things where if you turned it around on its side, you've got kilograms divided by meters cubed, and if we simplified that into what the units actually mean, we've got mass divided by volume, which gives us our equation, which is density here, which is a Greek letter called rho. Density is kilograms per meter squared. It can be in other values. It can be grams per centimeters cubed, whatever it's going to end up being asked for you to calculate. But if you're not told, I would go for kilograms per meter cubed. And mass here is in kilograms once again, and volume is in meters cubed. There we go. Simple. The whole of paper 1, all 11 equations that you need to know are done. Of course, if you're thinking, how can I revise all of these? How am I supposed to learn them all? The best way that I would go for is using something like Cover Write Check. I've also got a link to a document that you can use, which you can print out and make a flip book to revise these equations. But really, the best way to go back to learning these is just Cover Write Check, repetition, and do as soon as you've been told that you can start your exam, open the book, the cover of your paper, and on the first page there, write down all the equations you can remember, and that way you don't need to stress about them, and you can look back to your reference there for the equations that you could use. And then when you've come up to a calculation question, think about which one might be appropriate, and if in doubt, write out all the values you've been given with their symbols next to them, and think about which ones you might be able to use to solve the problem. But thank you guys for watching. Do check out my other videos, do like and subscribe.